Good morning, ladies and gentlemen, boys and girls, friends and neighbors. Let's have us a little discussion on polynomial functions. And we are only going to talk about polynomial functions of one variable. I know that previously we've looked at some polynomial expressions that had two variables. Well, these functions that we're talking about, they're only going to have one variable. So let's look at the definition of a polynomial. We're going to let the a, b, c, d, and e, we're going to let those be real numbers, and we're going to make sure that a does not equal 0. And n is going to be any non-negative integer. So n could be these numbers right here. Non-negative integers, so n is going to be something like this. 2, 3, ... Whole numbers, actually. So the n is going to be a subset of those numbers. And if you notice here, this are going to be the degree of the polynomial function n, and a is going to be the leading coefficient. So all of the exponents, what this means, if you have a polynomial functions, all of the exponents have got to be a whole number. And it would be silly to think about, you can have them, of an exponent being apologize for that interruption. So it's rare that the exponent of the polynomial is ever just 0. That's a rare case, but it can happen. So here's a polynomial. All of these a, b, c, d, and e, those are all real numbers. The only thing, stipulation, is a can't be 0, and that all of these exponents are and are non-negative integers. And so if n started out 4, n minus 1 would be 3, n minus 2 would be 2. Therefore, it's easy to look at a real example. So let's look at some examples of the polynomial functions of one variable and name the degree and the leading coefficient. So this guy right here, we see that all the exponents are non-negative integers. And here, a is going to be the leading coefficient, and the degree is going to be n. So a for this particular example is 5, and n is going to be 6, and this is the degree of this polynomial. So this is a 6-degree polynomial. Let me rewrite that 5 a little bit better so we can see it. And the leading coefficient is 5. For this particular example, for g here, a is going to be -2, and n is going to be 4, and this is our degree of this polynomial. Okay, that's the degree. And notice 4, 3, 2, 1. Notice 6, 3, 2. It doesn't matter. You don't have to go all of the 6, 5, 4, 3, 2, 1. We don't need that. And we've looked at dividing some polynomials where if you have a missing term, you need to put 0 in for the coefficients. So we've actually looked at some of these where some of the real numbers, b, c, and d, were 0. But for these two examples, I have the leading coefficient and I have the degree. I have the leading coefficient and the degree. Here are two examples of some functions that are not polynomials. This guy here is not a polynomial because I have the square root of x. Down the road, actually in the next large unit, we'll figure out how to write x as an exponent, but right now, that x doesn't have an integer. It doesn't have an exponent that's an integer, so this is a non-polynomial. And this guy here, we see this is a non-polynomial as well because of that -3. So the exponents of all of the x's have to be non-negative integers. Okie dokie. All right, so what I'm going to do is I'm going to jump forward, and we're going to have these notes. Hey, for these examples, we're going to find some specific points. Well, we know how to do this because we learned this last week for synthetic division, and we will come back to this later on this week, but we're going to forego this right now because we know how to do that. But I want to get to the end behavior, so I'm going to jump a few pages ahead here. Let's see where I want to go. I want to go down here, I believe. Yes. So I'm going to start talking about the properties of polynomials. Okay, these are properties of the polynomial function. The domain is all reals. That means the graph is continuous for all x values. Every x value has an output. Every x value has an output. And here's our x-axis here. I'm going to give you two examples. And polynomials are smooth. They're not absolute value graphs. They have no sharp edges or corners, no corners. Polynomials are smooth and continuous. So here's some examples of a polynomial. I'm not going to tell you which one it is, but so this guy looks like this. This could come up here, and this is smooth. I'm going to make a smooth transition, and then I'm going to come here. And what the domain all real means, that means it doesn't matter where you're going to go out here on the x-axis. It doesn't matter where you go if x gets really big. So like if x approaches infinity, that graph is going to have something that comes up to it. In like manner, if x goes to negative infinity over here, because keep in mind this is your x-axis and I have negative numbers, that graph will always have outputs. That's what it means to be continuous. There's an example of a continuous function, and there's that annoying bell again. Why they have those bells, I don't know. Here is another example of a polynomial function. Notice it's all smooth. It doesn't look smooth. It is. And notice that as x goes to infinity, always there's going to be an output. And as x goes to infinity this way, negative infinity, there's always, this just means as x gets really big, like say x is equal to 9,975, there's going to be an output for that input. That's what this means. And we're going to actually talk about this notation here. This notation is x arrows positive infinity, as x arrows negative infinity later on in this particular video. But that's just the example of a couple polynomials. Okie dokie. The other thing is, another nice property, all polynomials have y-intercepts. This is huge. This is a very important property right here. All polynomials have y-intercepts. How do you find the y-intercepts? You simply evaluate the function at 0. We don't need the synthetic division for this. We can evaluate these pretty easy. So here's a couple examples. This is a 6th-degree polynomial, leading coefficient 5. If I want to find the y-intercept, all I do is let x equal 0, and I'm going to put 0 in. Oh, look. If I put 0 in for all these x's, 0, 0, 0, 0, 5 times 0, 0, plus 7 times 0, 0, minus 2 times, all 0, that's going to be 12. And the y-intercept of this graph is going to be 0, 12. And we know the y-intercept of anything, it's going to have an x equals 0. Next example here, this g of x, if I want to find the y-intercept of g of x, I'm simply going to evaluate, put 0 in for x, and again, look what I'm going to have, 0, 0, 0, 0, negative 15. So the y-intercept of this particular graph is 0, negative 15. Okay? All polynomial graphs have y-intercepts. Some polynomials have x-intercepts and some do not. Hey, look what I'm going to do. And I'm going to show you a couple more examples. But if I go up here to look at these, what? This particular graph here, if I look at this dude, this guy has 3 x-intercepts. 1, 2, 3. This guy has 3 x-intercepts. This guy has no x-intercepts. This guy has no x-intercepts. This has 3 x-intercepts. Oh, look. They certainly both have y-intercepts. All polynomials have y-intercepts. Not all polynomials have x-intercepts. Alrighty. And we can come up with a couple more examples here. Here is well, this looks like a polynomial function that we've looked at, like a quadratic function where a is negative. What? This guy here has two x-intercepts. Here we go, right here. And it certainly has one y-intercept right there. And if you want a graph that doesn't have an x-intercept, we can do a graph that doesn't have an x-intercept, and here you go. Let's do it in purple this time. Whoa. There's a graph that doesn't have no x-intercepts. This graph has two x-intercepts. And of course, they both have y-intercepts. Okay. Pretty easy stuff right there, x and y-intercepts, the graph. Well, let's talk about something that's a little bit more detailed and confusing. So all polynomial functions have their own power function associated with them. Power function. Power function. What the heck is a power function? Here's a power function. A power function is a polynomial degree n where all of these guys, remember I was talking about that? B, C, D, and E are all 0. So a power function has one term. Has only one term. And here's two examples of a power function, f of x, 7x cubed. The degree of this guy right here, the degree is 3. The leading coefficient is 7. That's a power function. A power function only has one term. Here's, what about g? The degree of g is 2. The leading coefficient is -4. Power functions have one term. They have a leading coefficient, of course, and they have an exponent that is a non-negative integer. So I've got this power function and this power function. Why, might you ask, is a power function important? A power function is important because each polynomial, here I have a polynomial, this particular polynomial has a particular power function. All polynomials have their own power function associated with them. So this particular, here's a big old long polynomial. Its power function is 5x to the 6th. Its power function is its leading term. Why would I talk about the power function of a polynomial? Why would you do that? The reason why you would do that is because the function is going to look at the ends exactly like its power function. So you're telling me, Lee, that the graph of this is going to look like the graph? Yep, that's what we're saying. So let's just name these power functions for these, and then we'll get into more detail about the power function. And we're going to name, we can't really name them f. We're going to name it subscript f. The power function here is going to be 5x to the, 5x to the 6th. That's the power function for that function. Keep in mind, a power function only has one term. A polynomial's power function is its leading term. This guy right here, what is this? We're not going to call it g. We can't because this is g. We're going to call it subscript. G subscript x. The power function of this guy is -2x to the 4th. What? Yes, indeed. Again, I ask you, why Because the graph of a polynomial is going to look like the graph of its power function at the ends. What we're talking about is the end of the graph. What happens when x gets big and when x gets little? What does the graph look like? This is a complicated theoretical statement. If you don't want to look at this statement right now, you don't have to. If you want to look away from this statement and say, what? I don't want to look at it, that's okay. But we're going to give you an example that, I'm going to give you some examples of what the world this means. What is all this rigmarole here? Here we go. So let's see here. The end behavior of the polynomial describes what the graph looks like towards the end of the graph, Let's see here. Polynomial function looks like its power function. Well, we need some properties of the power function, and here we go. So let me do this right here. Okay, so here I'm going to look at a power function, and this is theoretical, ax to the n. The leading coefficient here is a, and the degree is n. If n is odd and a is greater than 0, i.e. a is positive, then the graph of the polynomial starts negative and ends positive. So let's do an example here. Example where n is odd. So let's go x to the 5th, and let's go a is positive. Let's go 3x to the 5th. Okay, we're just going to look at that particular rascal there. I'm going to tell you, boy, that's a bad line. Let me get him out of there. Let me do a nice line here. Let me do a straight line. There we go. What's going to happen? That graph is going to start negative. Well, I don't understand what start. Here's what start negative means. This is the negative part. This is the positive part of the graph. This thing is going to start negative. We don't care what happens on the inside. In fact, let me write this better this way. So this starts negative, ends positive. Down here is negative, up here is positive. And what we would say about this particular, here is a statement, and we're going to make some statements about end behavior. So for this guy right here, as x goes to negative infinity, here's x going to negative infinity. That particular function goes to negative infinity as well, because it's going down, it's starting negative. The other statement I can make about this is x goes to positive infinity. This function right here is going to positive infinity. So this guy is shooting off. As x goes to positive infinity this way, as x goes to positive infinity, the function, you can see, goes to positive infinity. And like manner, as x goes to negative infinity, that function goes to negative infinity. That 3x to the 5th. If n is odd and a is negative, so let's do another example. Let's do this example in black. So if a is negative, this is what a less than 0 means. A is negative. Give me an example, Billy, of a negative. How about negative 4? And let's go x to the 7th. Here n is odd and a is negative. What would that graph look like? That graph is going to start positive and end negative. Another way to think about this, so this is positive again, this is negative, this is negative x's, so I want to look at what happens when x goes to negative infinity. What it says is this graph is going to start positive, and end negative. We don't really care what it does in the middle, but it's going to end negative. And this time, as x goes to negative infinity, what's going to happen? The function is going to go to positive infinity. As x goes to positive infinity, the function is going to shoot down to negative infinity. And we're going to make a statement about that as well. Here's our statement. As x goes to negative infinity, this function here goes to positive infinity. That means if x is going this way, and think about this. If I had a really big number, if I evaluated h, here's another way to think about this. If I evaluated h at negative 9,999, what would that be? That's going to be negative 4 times this guy to the 7th power times this dude right here. Call it whatever you want to call it. Call it smiley face, green smiley face. Green smiley face to the 7th power. And this negative to the 7th power is going to be negative. Negative, negative is going to be positive. And that's why this guy is going to go positive as x goes to negative infinity. In like manner, as x goes to positive infinity, as x gets really big, that graph is going to shoot down there to negative infinity. Okay. So these are going to be very important. If n is odd and a is positive, the graph is going to start negative and end positive. If n is odd and a is negative, for example here, the graph is going to start positive up here and end negative down here. A couple more examples here. If n is even and a is greater than 0, do a couple examples here. A lot going on in this video, and that's okay. If n is even, let's do an example where this happens. N is even, let's see here, x to the 6th, and a is even 4x to the 6th. What's going to happen? The graph of the polynomial is going to start positive and end positive. So it's going to look like this. Start positive and end positive. We know it's going to be continuous, but I'm not going to talk about the end of this graph right here. What I'm going to do is make a statement. Whoopsie. I don't know what happened here. Oh, that'll work. And the statement I'm going to make is this. If x goes to negative infinity, the function goes to positive infinity. If x goes to negative infinity, the function shoots up. As x goes to positive infinity, the function shoots up as well. So as x goes to positive infinity, as x gets really, really big, the function is also going to get really, really big. Okay. Let's do the last example for end behavior. And why does that keep happening? I don't know. Let's do the next example here. Let me grab this on. It gets moved over this way. It does. Okay. Let's do the next example. Let's do an example where n is even. Let's go x to the 8th, and a is negative 2. What's that graph going to look like? Graph is going to start negative and end negative. Oh, let's see here. Come on. Okay, it's going to start negative and end negative. And what do I know? The statements are, as x goes to negative infinity, the function also goes to negative infinity. Function is shooting down. Here, as x goes to positive infinity, what's the graph doing? The graph is shooting down. End negative. Start negative, ends negative. So here's the graph. This is kind of all this red. I'm going to do the graph in green. And the other statement that I want to make is this statement here. As x goes to positive infinity, the function goes to negative infinity, sorry. Starts negative, ends negative. Why is that important? It's important because we want to analyze the graph of polynomials. So if I look at this power function and make a statement, this is your assignment. Your assignment number 1 is going to look exactly like this. Don't make it difficult. Here we go. For each of the following polynomial functions, find the power function and make a statement about the end behavior. Well, what's the power function of this guy right here? It's simply 5x to the 4th. Now I know that for that particular power function, a is equal to 5, which is greater than 0, and the degree is equal to 4, which is even. So if I go back, now I know what's going to happen. That guy is going to start positive and end positive. Why? Because of this rule right here. I have n is even and a is positive. The graph starts positive, it ends positive. So here's the statement that I'm going to make here. As x goes to negative infinity, the function f of x also goes to positive infinity. As x goes to negative infinity, the function goes to positive infinity. So this thing is going to start positive, and it's going to end positive. Do another example. For your homework, this guy right here, hey, what's the power function? The power function here is going to be 2x to the 5th. A is equal to 2, which is positive. N is equal to 5, which is odd. And if I look back in my notes, I will see that if I have n is odd and a is positive, let's go back there. If n is odd and a is positive, the graph starts negative and ends positive. So you might have to review this page. This page is going to be very important. So I'm going to make a statement. So I found the power function. A statement about the end behavior is simply going to be, as x goes to negative infinity, the function goes to negative infinity. Starts negative, ends positive. If the leading coefficient is positive and the degree is odd. As x goes to positive infinity, the function goes to positive infinity. This certainly will not be the only time that we look at the end behavior. There's a lot of information that came to you today. You might have to review this, and we will certainly review this in class. Tomorrow during our meet, we're going to talk about x and y intercepts in more detail. So hang in there, and we'll catch you on the flip side.